except for all the lightning class speakers, is Daniel Gross, who's giving his first in a series of 3.
Thank you very much. It's a great pleasure to be here. I'm having a terrific time. Thanks for the invitation to come and tell you some things. Here's my first version of what's a very naive question, and we'll refine this as we go. But here's a very natural question you might ask about your finitely generated group that you have. Is gamma the fundamental group of a closed aspherical manifold? Maybe we'll call this M sub gamma. And then, so this is part 1 of the question. And part 2 of the question is, if so, is M gamma unique up to, say, homeomorphism? Okay. So I claim that these strike me as very natural and important questions. So this is what we're going to focus on for the next 3 talks. So we heard from Nathan already that given any finitely presented group, it's the fundamental group of a 4 manifold, closed orientable 4 manifold. And that 4 can be replaced by any number greater than or equal to 4. Now, if you're going to be the fundamental group of a closed manifold, then you'd better at least be finitely presented. So let's assume our group is finitely presented. But assuming that your manifold is aspherical is a very strong assumption. So just going from is the fundamental group of a manifold to is it the fundamental group of a closed aspherical manifold changes the story completely. Okay, and that's what we'll start by talking about. Of course, this question here, I'm also asking about is the M gamma that is closed and aspherical and has this fundamental group unique up to homeomorphism. This second question is less naive than this question, and it has a name. And this so part 2 is called the Borel conjecture. It's known in many cases, and in general, it's open. So there are no known counterexamples to the statement that if 2 closed aspherical manifolds have the same fundamental group, then they are homeomorphic. Okay, so that's a uniqueness question. This is the existence question. The answer is not always. But it still has some very interesting aspects to it, the existence question. We'll eventually be focusing on the case where the manifold has dimension 3, because we're here this week to talk around 3 manifold groups. Okay, so observation. So an aspherical. So if M gamma, as Nathan mentioned, it should be a K gamma 1. That's just the name for an aspherical space that has the right fundamental group. And such a thing is unique up to homotopy. Homotopy equivalence, as you probably learn in your first algebraic topology class. You do if you take it from me. I don't know if you did in your first algebraic topology class. This is unique up to homotopy equivalence. In fact, if I have a map between 2 of these things, the homomorphism on fundamental group tells you the homotopy class of map. So it's not just that the space is unique up to homotopy equivalence. It's really functorial from groups to spaces up to homotopy equivalence and maps up to homotopy. And therefore, algebro topological invariants of such a space are actually invariants of the group gamma. So if I give you a gamma, if there's going to be an M gamma, then the homology of that and the cohomology of that and so on are going to be determined by gamma. So being a manifold tells you strong things about algebraic topology, in particular closed orientable N manifolds satisfy Poincare duality. So the ith homology of M with coefficients in your ring is isomorphic to the N minus ith cohomology of M with the same coefficients. And that isomorphism is realized by capping with the fundamental class. Something else you learn in that famous first course in algebraic topology. So this is something that, so you give me a group gamma, then there is a K gamma 1, and you can calculate its homology and its cohomology, and it may or may not satisfy this condition. Okay, and probably for your favorite group, unless your favorite group happens to be such a thing, if you just come across a group at random, it probably won't satisfy the homology. This probably won't satisfy this. So the right question is not this. The right question is, supposing that a group satisfies Poincare duality, then is it the fundamental group of a closed aspherical manifold? So I'm going to, in a minute, edit this question to be about groups satisfying Poincare duality. Okay, once I do that, I'm not going to do that until I tell you exactly what that means. But the upshot is, if I edit this question to say a group satisfying Poincare duality, once we know what that means, then this is also an open question. And so that's, and we'll particularly focus on that in dimension 3. So let me give you a definition that is not going to look like this. So gamma, a finitely generated group, then gamma is a Poincare duality group of dimension m, n. You should take the cohomology of gamma with coefficients in the group ring Z gamma. And if you've forgotten or don't know what that is, I'll remind you in a minute. And this should satisfy the following properties. It should be 0 outside of dimension n, and in dimension n it should be Z. And I'm going to consider all of my Poincare duality groups to be orientable. I'm thinking about orientable manifolds here. So this Z is a Z gamma module, and it could be a trivial or non-trivial module in general. I want it to be the trivial as a Z gamma module. Okay, so Z gamma is going to act trivially on Z. If it's if you have the fundamental group of a non-orientable manifold, it doesn't satisfy Poincare duality with Z coefficients in the naive way, and you have to think about the action on the orientation module, and that's non-trivial. So non-trivial here corresponds to non-orientable manifolds, and that's the last I'll say about that. Okay, so this Z is just Z. It's a trivial module. Okay, all right. So, and I'm going to abbreviate this to PDN. And the N is picked out, just like the N is picked out here, the N is picked out here as well. And so you actually, and so what is true is that fundamental groups of closed aspherical manifolds satisfy this. So we should have some examples after our definition. Example. So if M is closed, aspherical, orientable, N manifold, then pi1 of M is a PDN group. Okay, so that's the sort of naive and trivial examples. Although maybe from this definition, it's not so obvious that that is true. What other examples? So there are examples, and I won't describe these due to Davis. For n greater than or equal to 4, there exists finitely generated PDN groups that are not finitely presented. And since they're not finitely presented, they can't be the fundamental groups of closed orientable aspherical manifolds. And that's it, basically. We've basically exhausted the known examples of PDN groups. So this is an open question. It's known in some dimensions, it's known for some groups, but it's an open question in general. Just like this is an open question known for some dimensions and many classes of groups. Much more, I think, is known about this than about this. But I think of these as two sides of the same extremely natural question, which is just from group theory, can you tell whether there's a manifold floating around? Okay. All right, so I want to leave that question up for a minute. So I think this goes back to Wall. around the 60s. Yeah. Oh, sorry. It does actually. Yeah, it does actually. Yeah, no, so no. So by the way, you do need this to be for all coefficients, including twisted coefficients and so on. So you're not allowed to just say, I can take coefficients in a field or a ring or the integers or whatever to have all the points. But everything is encapsulated just in this definition here. Once you have this definition here, then you have Poincare duality, and I'll show this in a few minutes. You have Poincare duality in this flavor, but with gamma for arbitrary Z gamma modules. And there is a class, and coupling with that class does induce that isomorphism. So all of that comes to you out of just this one single definition. That's why this is a nice definition. Sort of cohomology with Z gamma coefficients captures everything. You should think of this as being like the compactly supported cohomology of the universal cover of the KG1. That is another way of thinking about what this is. And so if this were Rn, say, because you were some kind of an aspherical N manifold, then that's exactly the compactly supported cohomology of Rn. That's the definition. And in not very long, I'll tell or remind you of the definition of what this is and show that it implies such a statement. But at first I wanted to just, there's two questions that I've posed. The Wall question. I don't know that Wall conjectured that the answer should be yes. I don't know of that, I think, but he certainly asked it as a question. This is known as the Borel conjecture. So it's true if n equals 1. That's easy. Yeah, this is Wall, and then this will be Borel. And it's true for n equals 2, and this is really due to Ekman, and some collaborators of Ekman. And maybe we'll see a little bit more about that later, but probably not. And otherwise, it's open. There are groups for which it's known to be true. In high dimensions, this is actually very closely related to surgery theory, which tells you the classification of topological manifolds in higher dimensions. I am not an expert in surgery theory, but I believe the words you're supposed to say are correct. An answer yes to both of these questions is equivalent to the where we're using Z gamma is equivalent to the vanishing of the total surgery obstruction, which is something in algebraic L theory. Anyway, in dimension 3, we'll see it's not about surgery theory. Well, it's much more related, I think, to things about 3 manifolds that we've been seeing. So we'll get to that. Borel is known for n less than or equal to 3. Again, for 1, it's easy. For 2, it's the classification of surfaces, and for 3, it's a little bit harder. So maybe n equals 1, 2. Easy. N equals 2 here is harder. You just have the group and you have to build a manifold. You might worry that there's some weird group that satisfies this homological condition, but where did you find the manifold from? So the existence question is definitely sort of at least naively harder than the uniqueness question, because here at least you have a manifold. N equals 3, this is a consequence of geometrization. Plus, you need Waldhausen for or rather, Waldhausen already did it for the Harkin case. Plus, there's, I think the only other name I need to mention is Scott. There are some non-Harkin, non-hyperbolic manifolds. We haven't seen much about them yet. Small Seifert fibered spaces, where before you pass to the finite cover that Nathan was talking about, it's not a surface, but rather a rigid orbital. And we'll see some more of those on Thursday in my talk. And Scott proved the uniqueness of such things, given their fundamental group in the 80s, long before geometrization. And I don't think geometrization itself will give you that. But anyway, I think so. Nathan, is that true? You still need Scott even post geometrization to do the Borel conjecture? Yeah. Yeah, I think you do, but I'm not sure. Okay. All right. Okay, I'm going to erase my questions. There's 2 questions. I'm not going to talk more about the Borel conjecture. really, because we're going to focus on n equals 3. The Borel conjecture is known when n equals 3, and I'm not going to say more about that. The wall conjecture is open when n equals 3. Okay, and I'm going to try. Yes, Danny?
Abstraction in mathematics. It's good hand source examples of PV3 groups that you didn't already know were manifold groups.
No, I think Wall's question probably has a positive answer. I think it. I mean, I think of it as a way of putting 3 manifold topologists out of work. Right? It says you only need to do group theory. Sure.
Even a devil.
Yeah.
You're asking a question about stuff, but what examples do you even have of these things?
Well, the conjecture is that there are none, and so yeah, okay, maybe I'm going to spend the next 2.5 hours telling you that things that can only be the way that the other mini courses tell you that they are.
You can have like here's this group that I know was a PV3 group without already knowing that it was a 2 manifold.
No, no, I have no such examples. Yeah, luckily that's not how I do math.
I am not going to say anything else. I support it. I think it's great. I mean, you can as well.
Yeah, okay, thanks. If you have some examples, I'd be happy to play with them.
I don't think there are any homeomorphisms. Hopefully, solutions that are not obviously homeomorphisms there. So maybe
yeah, well, so yeah, I mean, what Davis did was sort of like that, but I mean, he uses Best-Wiener Brady-Morse theory and the Davis construction, which was built in order to do that, and that's great. And I mean, one of the reasons we don't have such examples in dimension 3 is that 2-dimensional topology is pretty nice, and so one of the things that you do is build things into links that are kind of pathological, and that's what Davis does in order to build things 1 dimension higher that have nice or bad properties depending on your flavor. And 3 is just too small a dimension to be able to start with something interesting in dimension 2, and we'll sort of see that. Yeah. Okay. All right. So that's that was my sales pitch, and then Donnie just demolished it. And so you can now choose whether you want to continue, because I've told you what I'm going to do, and Donnie's told you why you shouldn't care. So. All right. So let me remind you or tell you. So here we have the cohomology of a group, and we're also going to be interested in the homology of a group. And the way I usually think about this is to take a K gamma 1 and take its homology or its cohomology. But here we've got coefficients in a gamma module, and it's a little less clear topologically what that means. You can make sense of it, but I think it's clearer to see what this means algebraically than topologically. So let me just remind you of that. So to calculate homology of gamma or cohomology of gamma, you should start with projective resolution. I'm going to calculate the gamma. Donnie made his choice. That's all right. I don't have any red, and I'm not doing any topology, so I don't need colors. So we take Z, the trivial Z gamma module, and we take a projective resolution of it. And I always like to think of this as given by free modules. I'm going to stop in dimension n. Just let me do that. And I'm also going to pretend that all of the FIs are free, and I hope you'll let me do that as well. But really, they might have to be projective. If gamma has a finite K gamma 1, finite CW complex K gamma 1, then you can use that to build a finite resolution by free Z gamma modules, and that's what you should have in mind here. And then you should do one of two things. You should apply either. So I guess we're going to do should either tensor over Z gamma with M to the resolution, and that will give you a new chain complex. So you take this resolution and at each stage you apply this functor, you get a new chain complex. You delete the Z term. That's not somehow telling you anything interesting. And then you calculate the homology of that complex. So that gives you, when you do that, the homology of gamma with coefficients in M, where M, in order that we could do this, had better have been a Z gamma module. Okay, so it's a thing you can do. On the exercise sheet, I sort of explained how you might work out a couple of examples of this if you have never done it before or it's been a while. The other thing you can do is apply that functor, hom to M as a functor. That gets you another chain complex. This is a covariant functor, so arrows continue to go in this direction. When you apply hom, it's a contravariant functor, so now arrows go in this direction, and that's why we're going to calculate cohomology. So you get a new chain complex, you still delete the Z term, you calculate homology, and that's going to give you the cohomology of gamma with coefficients in your favorite Z gamma module M. Okay, so this is all, for example, in the first couple of chapters of Brown on cohomology of groups. And it's going to give you the same thing as the calculation that you made with the K gamma 1 using topology, if that's what you prefer. All right, so here's a theorem. Gamma finitely generated group. So gamma is, and I guess I should fix my N. Gamma is a PDN group. If and only if, so now we need for all Z gamma modules M, there is an isomorphism between the I, and for all I, there is an isomorphism between the I homology of cohomology of gamma with coefficients in M and the N minus I homology with coefficients in M. So this is actually a true statement, to hark back to Shelley's question. It is also true that there is a class in the nth homology that is the fundamental class, and capping with that fundamental class algebraically induces this isomorphism, and that's a consequence. But we're not going to need that. So it is actually an if and only if there is such an isomorphism, and then if and only if there is an isomorphism that is induced by capping with a fundamental class. Okay. What's that? I'm assuming finite generation. Yeah. No, somebody said. Yeah, I was going to say yes. Does this condition imply that these groups are finitely generated?
Example, which is finite generated.
It is FP2. So it has, yeah. Yeah, so Davis used Best-Wiener-Brady-Morse theory with a finitely generated group that's not finitely presented, but is FP2, and then manifolded it with the reflection group trick. So it has all sorts of nice homological finiteness properties. Yeah. I was going to sketch this. I think I have time. Actually, I'm going to sketch this direction. The other direction is not much harder, but I assigned it as a homework question. I don't know if that's reasonable. I don't care if you do the homework. So it's a nice exercise. It's not very hard. But if you don't want to do it, I'm not going to force you. We're not going to do a lot of homological algebra after the next board of work. Okay, so and I'm going to assume gamma has type F, which is said as a finite K gamma 1, and that means I have a resolution of finitely generated free Z gamma modules over there, instead of generally they might be projective and so All right, so let's see. I have my resolution. I'm going to put the FN here. I claim that I can do that. Let's not worry too much about that. So I claim that my resolution can stop at degree n and be 0 afterwards. Let's not worry too much about that. So now I'm supposed to apply, and these are all free. I'm going to apply hom blank z gamma. Okay, so I can do that. And that's going to calculate the cohomology of gamma with z gamma coefficients, which is the thing I know something about. Okay, so I'm just going to write fi star as hom fi z gamma. Okay, it's a dual. Okay, these are free modules, and I'm just mapping it into there. It's an obvious dual. So star f1 star. Maybe here I should go to fn minus 1 star fn star. All right. Well, I just took a free thing and a free z gamma module and applied hom blank z gamma. So these are all free. Okay. And not only that, this complex is exact everywhere, because remember, hi gamma z gamma is 0 or z. So this complex is exact everywhere except where? It's exact everywhere except here. Okay. So here, the homology is z. So what does that mean? I have a map here, d and star, and then that maps to 0. And when I factor out the image, I get z. So I can replace this by the image of d star mapping to z, mapping to 0. Okay, so I have a bunch of free things, and it ends with z. And remember, this was a trivial z gamma module. So what do I have here? I have a free resolution of z by free z gamma modules. All right. So this is exactly the sort of thing that I started with. Okay, I didn't do anything. All right. So, well, you delete that. You delete the z term to go. Right. When you calculate the homology, you don't dualize the first term. You delete it. Right. Just the same here. You delete this, because otherwise h0 would be 0. Right. So I'm not doing reduced. Right. So this 0 vanished. So sorry, but there was a z here. Yes, you're right. There was a z here, and then when I went to here, it vanished. Yeah. Sorry, I forgot.
You want to write the image and then z, or just to add the z?
Did I not want? Sorry, doing homological algebra on the board is not my forte. Maybe I should have written the kernel here. No, I think I was supposed to write the image. That was right before. The kernel of this is everything. The kernel mod the image is z. So I map to, what do I map to? No, I'm supposed to map to fn star. Yeah. Okay. And then I factor it. Sorry. Yeah. So now this is exact when I do this. I'm sorry. Yeah. Should have stopped and checked my notes before I did that. Okay, great. So this is exactly the sort of thing that we started with. So now to finish the proof, I'm going to calculate. So to apply cohomology with m coefficients, I'm supposed to apply hom blank m to this. Okay, so I can do that. Or I could have done it to this, because this is also a free resolution and it doesn't matter which one I take. To get homology, so I'm going to get homology from here by applying tensor product with m, and I'm going to get cohomology from here by applying hom blank m. Okay. And all you need to notice is that, well, if I take any guy and tensor hom blank z gamma over z gamma with m, then that may as well be hom over gamma of pm. Okay. So that's just the standard duality for tensor product and hom. And so if I apply hom blank M to this, I'll get cohomology. And if I apply the tensor product with M to this, I'll get homology. And those groups will just be the same groups, and I'll run them in different directions. And then that proves this statement here. Okay. So that was much less clear than it would have been if you had somebody who was actually good at homological algebra doing that for you. But it's really not that hard. It's probably better for you to do it yourself. Okay, very good. Right. So this strange condition that I gave you about being a PDN group implies this condition that looks much more like Poincare duality. In fact, the converse is also true. And there, I set that as an exercise. Okay. All right. Very good. So let's introduce some geometry. So I'm going to focus on n equals 3, but I'll still say something about hyperbolic groups. Here by hyperbolic groups, I mean Gromov or word hyperbolic groups, which we haven't seen yet in this conference. And I'll explain why this is a case that you might like to think about in a bit. So gamma finitely generated group is Gromov hyperbolic for a Cayley graph, let's say C of gamma, as Michelle had, of gamma, with respect to a finite generating set. There exists a delta such that for all x, y, z in C gamma with geodesics x, y, xz, yz, we have that the third geodesic, which happens to be xz, is contained in the delta neighborhood of the union of the other two. That's when I probably should have some colored chalk. So here I have x, and I have y, and I have z, and I have a geodesic. That's the third one, so I want to draw that last. So I have the geodesic from x to y. This is just a geodesic in the graph metric on this Cayley graph. And a geodesic from y to z, and I take the delta neighborhood around those two things. And if I hadn't have done that first, then the geodesic comes in and it stays inside that neighborhood. So this is delta. So normally I make a joke about how you have to be careful to draw the third side last, but I wasn't careful, and then the joke's on me. So, all right. So this is a very important class of groups, and we haven't seen any of them yet this week. But for us, a motivating example is gamma is pi1 of m, where m is a closed hyperbolic 3 manifold. 3 can be replaced by any other n that you like, and many other groups as well. This property here is an abstraction of a property that is just true in real hyperbolic geometry, which is that triangles are thin. And that's a pretty easy consequence of the fact that the area of triangles, of any geodesic triangle in H2, is bounded by pi. Okay, and this is an abstraction of that, and it's a very powerful and useful abstraction. Okay. So here's some geometry, and associated to, I'm just going to say a hyperbolic group. I'm not going to keep writing Gromov hyperbolic, but I want to make clear that although Donnie will think otherwise, we don't know that our hyperbolic PD3 groups are 3 manifold groups. Okay, maybe they all are, but we don't know. So associated to a hyperbolic group, gamma is a boundary. So the boundary of gamma comes from geodesic rays. So mapping the non-negative reals into, let's just say I continue with our Cayley graph, modulo an equivalence relation, and that equivalence relation is just a bounded Hausdorff distance of the images. So here are some. So another example of a hyperbolic group is a non-abelian free group or any free group. And then the boundary of gamma is a Cantor set. And you can sort of imagine that from the Cayley graph, taking the Cayley graph to be a tree, and then you're thinking about the ways out to infinity in a tree, and then the natural boundary of the tree that we saw today in Ian's lecture will be the same boundary of that tree. This is not a rooted tree, doesn't make any difference, it turns out. On the other hand, I1 of M closed hyperbolic n manifold, then the boundary of gamma is naturally around n-1 sphere. So I'm not going to tell you how to put a metric on it. That's a different story. Okay, in particular, for n equals 3, you get a 2 sphere. Okay, and from the point of view of PD n groups, well, here's a theorem due to Bestvina Mess, and Bestvina had a paper making this a little more explicit. So if gamma is, let's assume away torsion free, because otherwise we don't have a chance of being a fundamental group of a finite dimensional aspherical space, torsion free and hyperbolic, then gamma is a PD3 group if and only if the boundary of gamma is this thing that we would have got from this example up to, now this is just up to homeomorphism. There's no metric statement here. For higher dimensions, you have to replace sphere by homology n-1 sphere. And this is sort of where the niceness of dimension 2 comes in. Any homology 2 sphere is actually a 2 sphere. But in higher dimensions, that's no longer true. So you might have hyperbolic PDN groups with things that are homology spheres, but not actual spheres. All right, so here's a case of Wall's question. If gamma is torsion free, torsion may or may not be an issue for this question, we don't know, hyperbolic group, and boundary of gamma is a 2 sphere, is gamma closed, I should say orientable here, and hyperbolic. Is gamma already the fundamental group of a closed hyperbolic 3 manifold? Okay, so that's a case of Wall's question. I'm going to try and convince you that it's an interesting case of Wall's question. Okay, yes. So in order that it be a PD3 group, it has to be torsion free. And that's why I wrote torsion free there. For all we know, this, if I delete torsion free here, this is still an open question. And for all we know, it's true for torsion free groups. And if there's torsion, it's not true. That's all I mean by it may or may not be an issue. Right. So
Virtually, it would be virtually.
it could be an orbifold, it could have a finite center. Yeah. So there are some virtual type issues. If it has torsion. Yeah, that's the other thing as well. Yes. Yeah. Normally you would say, is it Kleinian, meaning is it a discrete subgroup of PSL2C? Then there would still be an issue about a finite center, which you might have to mud out by. Okay, so up to these issues of torsion free and whether it's an orbifold and whether there's a finite group and so on, this question is usually called the Cannon conjecture after Jim Cannon. And it was originally envisaged as a way of attacking geometrization, to see some coarse geometry in the fundamental group of a 3 manifold first, and then having found that coarse geometry, upgrading that coarse geometry to actual real hyperbolic geometry. Okay, so sort of that's part of a 2-step program to part of geometrization, which is not how it was done at all at the end. Okay, that's historically where Cannon came up with this. He was interested in understanding what Thurston was doing and also interested in discrete groups, and he abstracted some of these properties to see that this was a question that was worth asking from this point of view. Okay. All right, great. We'll spend some of Thursday and most of Friday talking about this question and related questions. But I want to focus for most of the rest of today, maybe all of the rest of today. I'm not going to explain why this is true. by the way, but I'll say 30 seconds about it in words without saying anything. Associated to a hyperbolic group is a thing called the Rips complex, which you also act on, and it's locally finite, and it's a cell complex. If you're torsion free, you act freely and co-compactly on it. So that's a K gamma 1. What Bestvena and Mess and Bestvena show is that adding the boundary to that is a very nice thing to do. It's a compactification, but it's a compactification that's very nice from the point of view of homotopy theory, and that allows them to get a duality statement between the cohomology of the group. So Bestvena Mess do the cohomology of the group with group ring coefficients versus the check cohomology of the boundary one dimension down. If it's a manifold like this, then that's just the ordinary cohomology of the boundary. And so you can see exactly where this statement comes in from that. But most boundaries of hyperbolic groups are not manifolds. They're really terrible spaces. Ordinary homology is not the right homology. Ordinary cohomology is not the right cohomology. You want check cohomology or Steenrod homology. So Bestvena uses Steenrod homology, which is the dual theory to check cohomology, and shows a similar duality statement about the Steenrod homology of the boundary versus the homology of the group. And that's what allows you to see that this must be a homology n minus 1 method. It uses the Rips complex and the fact that the boundary nicely compactifies the Rips complex as what's called a Z-set. Okay. I think they both need that correspondence. Yeah. I don't think either of them's easy. Non-hyperbolic PD3 groups. Okay, so my idea about understanding this question of wall should be, well, maybe we're trying to prove that it's true. So we have all of this structure that we know about all three manifolds. I'm assuming my three manifold is aspherical if I'm aiming at something. And so I don't have to worry about prime or irreducible or finite fundamental group. The fundamental group will be infinite, and the manifold, if it exists, will be aspherical, and so on. So we should be aiming at the structure that you see from the geometrization theorem and the JSJ decomposition, which, as we saw, are related but not quite the same. And so one might ask, is there an analog of JSJ decompositions for three manifolds in group theory? And the answer is yes. And actually, I think this is the first place that theory arose in group theory. Was a paper of Peter Kropholler about an analog. It's called an analog of the torus decomposition for Poincare duality groups. And he says, okay, well, just assuming the Poincare dualityness of your group and not the three manifoldness of your group, you can still say a lot of the things towards geometrization. I think the actual statement. So this is a theorem, and it's due. I think the Kropholler, and I think the actual statement that I'm going to make is maybe in paper of Dunwoody and Segev. But in the meantime, Zleel really brought JSJ decompositions to bear on groups in general. For Poincare duality groups, Kropholler sort of had this earlier thing. So here's the statement: gamma PD3 group. So either one of two things happens. So either one, gamma is already a fundamental group of a three manifold, closed, aspherical, orientable, and it will be either of Sol geometry or it will be of Seifert-fibered geometry. Okay. So that's one case. And in particular, notice it's already a three manifold group and we've won. Okay, so we have nothing more to say here if we're just trying to answer Wall's question. Or two, there exists a graph of groups decomposition, which you should think of now as a JSJ decomposition of groups of gamma with Z-squared edge groups and vertex groups which are either Seifert-fibered, so fundamental groups of Seifert-fibered three manifolds, now with boundary, and those boundary are tori, or atoroidal. Nathan defined atoroidal for three manifolds. Here I want it to be atoroidal in a group theoretic sense. So atoroidal means, So the vertex group is atoroidal. Every z squared subgroup is conjugate into an edge group. Okay, so a torus is a z squared subgroup in this geometric group theory point of view, and the only z squared subgroups of these vertex groups are already in the edge groups. So there's a cartoon like. So maybe I'll draw it as a graph of groups. There's a z squared subgroup, but this is a cartoon that's very much analogous to the cartoon that Nathan drew yesterday. So maybe it's got some atoroidal pieces, and maybe it's got some fibered pieces, and they're glued together along these tori, these z squared subgroups. Moreover, if you knew that the atoroidal pieces were fundamental groups of three manifolds with boundary being the z squared subgroups, then you could glue these three manifolds from the Seifert fibered pieces and the three manifolds from the atoroidal pieces together to get a closed three manifold that would have gamma as its fundamental group. Okay, so I really mean the fundamental group of a Seifert fibered three manifold. Yeah, and I'm going to sort of explain where that comes from partly in Thursday's lecture. But yeah, that's right. I really do mean it's already the fundamental group of a Seifert fibered three manifold. Yeah, so these pieces are three manifold pieces. These pieces are probably, we don't know, but probably they are, but we have no idea. They're glued together along z squared subgroups. They're coming from boundary components in some way. If you could solve the question for these, then you would have solved the question. Yeah, Dave. Yeah. No, the trivial graph of groups decomposition, where there are no edge groups and one atoroidal vertex group is allowed. Yeah. No, that's not, well, okay, that answers the question of what I'm going to do with my last 5 minutes. There's two things I want to do. One is sort of make explicit how this reduces the problem to something about atoroidal things and exactly what that means. And the other is actually, I want to explain from a different point of view how little we know about PD3 groups. But maybe I'll start with the how little we know on Thursday. Yeah, conjugate by an element in the vertex group already. Yeah, so maybe just to be explicit definition, so GP, where P is some collection of z squared subgroups, atoroidal if every z squared contained in G is conjugate into P. It doesn't have to be an element of P, it could be a finite index subgroup of an element of P, because of course z squared has many z squared subgroups. So really there are now two, which is really three questions, but two questions that you might ask are one, atoroidal implies hyperbolic, and then that would be, is that the Cannon conjecture? If there are these z squared subgroups, you are not going to be a Gromov hyperbolic group, just like for Nathan, closed hyperbolic three manifolds don't have z squared subgroups, then you should be like a finite volume hyperbolic three manifold, and the geometric group theory analog of that is what's called relatively hyperbolic, and we might see some more of that, but not in the next 2 minutes. So that's a question you could ask. If you have a vertex group of this graph of groups decomposition, and it is an atoroidal piece, is it a relatively hyperbolic group? Is there some geometric group theory geometry that you can associate to it? And then to Dave's question, if the graph of groups was trivial, there would be no z squared subgroups because there'd be no edge groups. And then you'd be asking really, is it hyperbolic? So this is relatively hyperbolic, should be relative to this family of edge groups. That should be what your relatively hyperbolic groups come with a peripheral structure, and it should be these edge groups that you get. If there are no edge groups, empty structure, hyperbolic group. So that's a conjecture that has nothing to do with the Cannon conjecture. It's sort of orthogonal to the Cannon conjecture. And two is then the relatively hyperbolic group implies pi 1 of M, and now M should be finite volume. The sorts of things that occur in the geometric decomposition, finite volume, hyperbolic three manifold, and you should hope, and it will be true, that your boundary components correspond to edge groups and so on. And again, if there are none, it should be a closed hyperbolic three manifold, and that would be the Cannon conjecture. So there's these sorts of, and they're really, each of them a two-part question. One, this absolute statement: if there are no z-squared subgroups, are you a hyperbolic group in the sense of Gromov? And then if you are you a real hyperbolic three manifold? And then the relative statements when you have these peripheral subgroups. And I'll be more specific about the relative statement here later in the week. As far as I know, well, in the case where there are boundary components, knowing how to do this is part of Thurston's Harkin geometrization in the Harkin case. In the case where it's a toroidal has no z-squared subgroups at all, because this is trivial graph. There's no proof of this in the three manifold setting that doesn't go through parallel. This is something that's out of reach without parallel type techniques. As this is in the three manifold. You have a question there? Yeah, I was going to come back to that later. The answer is yes. Yes, there's an if and only if the Bowditch boundary is there's a two-star Genevieve with and there's another proof by over one. I'll come back to that. I'll come back to that on Friday. PD3 groups start and then we'll say something about some of these things for the next group. My head, off the top of my head. Yes. Yeah. Yes. So I'll get the definition. Let's just say I have one subgroup. It doesn't matter. It's a GH. This is a definition. It's a PD and pair. If when you double G along H, this is a PD and group. And if you have a family, you double and the whole family. So that you can take that as a definition. It's not a very satisfactory definition because you want a homological definition. So you can make a homological definition in terms of pointary duality of relative homology versus cohomology, relative cohomology versus homology, the usual statements about boundaries, and that it's equivalent to this. Okay, because you can do Maya torus and so on. And so you can sort of see from this how to get between them. Because they're finitely generated but not finitely presented. Well, everything, yeah, I mean, everything's the fundamental. Yeah, probably, but I don't know. Yeah, but if you're not closed, you don't get pointary duality.
Doesn't detect finite integration.
Correct.
Only finite integration.
That's right. Yeah. I don't know is the answer, but I'm not interested in non-closed manifolds except for manifolds with boundaries. Did you have a question, Sam?
Yeah, knowing about Israel's properties.
Yeah, that was one of the things I was going to start with in my list of things we don't know. We don't know if PD3 groups are residually finite. In fact, we don't know if there exists a proper finite index subgroup of everyone. We don't know. We basically don't know anything about PD3 groups in general. So this is sort of an optimistic story that you feel like you can start using three manifold techniques and so on and start getting your hands into things. But there's a pessimistic story, which is we know nothing about PD3 groups in general. We don't know if they're coherent. We don't even know if they're almost coherent. We don't know if they're residually finite. We don't know if they have surface subgroups. We don't know. We know a few things in general, but we know very little actually. Well, that's the question. That's the question, and Danny already asked that. Yes. So.
All right, maybe we'll end the first there. At 3:30, there are problem sessions. Anything about that?
Yeah. Couple of quick announcements about what is happening later today and also tomorrow morning. So right now outside, hopefully there should have appeared magically some amount of snacks, including fruit, so that we'll have a break. At 3:30, we have problem sessions for Daniel's and Michelle's courses, the one in this room, one across the hall. I don't have any strong preference about which one's where, but we'll have two problem sessions.
Make a decision now and announce it.
Daniel's standing here. Daniel's course will be here. Michelle's course will be across the hall. At 4:30, there will be lightning talks. Thank you, Thomas, for chairing the lightning talks. If you're speaking today, then you've emailed me about it and you know who you are. I can give the full list if people want, or you can just show up and be surprised by, several great talks.
How long is it?
5 minutes or less than or equal,
5 times 1.
5 times 7 plus transition times.
So it'll be done in 30 minutes.
Tomorrow morning, we start at 9 a.m. 9. 9:30.
Not QAM, 9 a.m.
So thank you for coming a little bit earlier. But you'll have the
Daniel again.
A muffin with the cookies are hidden underneath the table.